Are we recording?
Yeah.
Yep, great. So good morning and welcome to this Clarity Prediction Challenge webinar. So the purpose of this webinar is for people interested in taking part in the Clarity Prediction Challenge that we're running, to give you a little bit of information about the challenge and to provide you some background. So I'm John Barker, and I'm here with a number of colleagues from the Clarity Project. You can see a long list of names on the front there. We'll be jointly showing this presentation, talking you through the challenge, and there'll be an opportunity for Q&A later. So, a little bit of background. So the Clarity Challenge has been organised by the Clarity Project, which is a 5-year funded project run in the UK. The point of this project has been to bring together a number of different communities, in particular signal processing, speech technology, hearing science and machine learning, with the aim of developing better algorithms for hearing aid for handling speech and noise. And we're particularly interested in the problem of speech and noise and intelligibility. So there are estimated to be by 2035, 15 million people with hearing loss in the UK. And this is a worldwide problem. It's not just specific to the UK. And speech and noise remains one of the major problems for hearing aid technology. So, with speech in quiet conditions, the amplification provided by the hearing aid means that people with hearing deficit can handle the speech well. But as soon as you're in a noisy environment, amplification isn't enough. The noise gets amplified as well, so you have to do some sort of source separation. And hearing aids, have not been shown to provide as much benefit as people would want in that kind of condition. So at the same time, there's been advances in machine learning that have transformed speech technology in the last 10 years. So people who are familiar with automatic speech recognition will have seen in the last 5-10 years have been huge advances, end-to-end systems, deep learning, that are able to do a very good job of separating speech from noise and then doing speech recognition. So this project is kind of bringing these communities together to try and bring some of this technology into the hearing aid space. So it's a 5-year project, and through this project we are organising a series of challenges. So I'll just explain what I mean by these challenges. There are 2 types of challenges that we are organising. Enhancement challenges, which are all about taking noisy signals and trying to enhance them for the benefit of hearing impaired listeners. So this is kind of like producing the actual hearing aid signal processing itself. And then there's the prediction challenges. And the point of these is, if we've got a noisy signal, can we predict how well a hearing impaired person will be able to understand it? And the reason we're running these 2 challenges together is because they interact. So having good predictive models is really important for people trying to develop new enhancement systems. If you're a machine learning person trying to make an enhancement system, you need an objective function. So what you want to be able to do is predict how well your enhancement is going to work. And for that, you need to be able to predict how well it's going to work when the signals are presented to a hearing impaired listener. So the prediction challenges provide the objective functions for the enhancement challenges. At the same time, enhancement challenges end up with us doing lots of listening tests to evaluate systems. So people submit systems for the enhancement challenges. We send them to panels of listeners, which gives us lots of scores from these listening tests, and that provides the materials that we need for the prediction challenges. So these 2 sets of challenges are kind of running in lockstep, and we will be discussing this a little bit further as we go through this session. So we're going to run 3 rounds of these challenges over the first 5 years. The first round launched last year, and we've already completed the first Clarity Enhancement Challenge. It launched back in 31st of January. We released training data, development tools, and testing conditions. In April, we released testing data and teams submitted their results in May. So we had a number of teams developing different signal processing strategies for hearing aids. In this challenge, you're given a signal and you're given an audiogram for a listener. You have to enhance the signal for that audiogram. Then your enhanced signal is presented to that listener. And then we have this evaluation phase in between May and September, where we had a panel of hearing impaired listeners listening to all these signals and ranking the systems according to intelligibility. And then we ran a workshop event in conjunction with Interspeech last year in September to announce the winners. So at the same time in the enhancement challenge last year, we had a baseline objective measure. So we had two parallel challenges. One was to provide systems which produce the best objective measure scores. And for the objective measure, we're using something called MB-STOI. And the other was to produce the best actual listing test scores. So obviously, the current prediction challenge is all about making better objective measures. Last year, we ran the first enhancement challenge. We were running using MB-STOI as the objective measure. This is a kind of, if you like, off-the-shelf, kind of state-of-the-art objective measure at the time, the best we kind of knew how to do. And part of the purpose of the first enhancement challenge was to see how well it's actually correlated with actual listing tests. What you can see here on the right is MB-STOI evaluation scores for all the teams that entered, where a high score is good and a low score is bad. You can see the baseline scoring about 0.28. All the entrants managed to improve on the baseline objective score. But then what you can see then below is the listing test evaluation. And you'll see again that all the systems actually improve the intelligibility in the listing tests above the baseline. But what you'll see is that the MB-STOI ranking does not correlate well with the listing test ranking. So MB-STOI is not a good predictor of the actual listing tests. So this is kind of the nub of the problem. This is really where the kind of prediction challenge takes off. So 10 systems were evaluated by a panel of 28 hearing impaired listeners over a range of conditions. I mean, that has given us thousands of listening test responses of processed noisy sentences. So in the current prediction challenge, we're using this data, we're using these listening test responses, and we're asking people, can you build a better objective measure that can actually predict the observed sentence intelligibilities? So in this webinar, we're going to have a number of presentations. First of all, Trevor Cox is going to be talking a bit about speech intelligibility models and what speech intelligibility models do and how they're formed. And then we're going to have Michael Ackroyd is going to be speaking about hearing impairment and speech intelligibility. So how listeners perceive corrupted speech signals. And then finally, I will return to the actual clarity prediction challenge itself, talk a bit about the data, the tasks and the timeline and what entrants need to do. And then later on, we're going to have a Q&A session. So I think at that point, I will turn directly over to Trevor Cox. And we'll have to swap the screen share. Okay, thank you.
Thanks very much for that, John. Just shout if you can't hear me clearly. I'm going to do a short talk here on speech intelligibility metrics, which is, after all, what this prediction challenge is all about. So I guess we need to define what we mean by it, because you can have a variety of subtly different definitions. But in our case, we look at the percentage of words in a sentence that a listener identifies correctly is what we're using for our measure of speech intelligibility. And the reason this is useful is it captures a listener's ability to participate in a conversation when the signal is changed. It could be background noise, room reverberation, or in our case, processed by a hearing aid. Hopefully that improves the speech intelligibility, but of course it may create artifacts that harm speech intelligibility as well. And we're interested in objective speech intelligibility metrics here because we need to allow a computer to estimate the speech intelligibility in an optimization process if we're to improve hearing aids. Some of the uses, John's alluded to a few of them, but I guess the main primary reason people keep developing these is that listening tests are difficult and take a long time. So we need something that can be done automatically. And we use that in design and specification audio systems, whether that's a public address system in a railway station, or in our case, a hearing aid. It gets used in room acoustics design. And as John said, it gets used in target functions for optimizing speech processing, let's say speech enhancement. You can use it to evaluate hearing aids, and there's other uses like clinical phonetics that I know very little about, and so I won't touch on in this talk. So comment metrics have got weaknesses. As John says, the correlation with our data isn't very good. We collected in the first enhancement challenge, but in general, we find that most are monaural, but we need binaural metrics, ones which work by the fact we have 2 ears and can use binaural unmasking. Most of them start by assuming we have young adult hearing, but we're working with people with a hearing loss. And we're working here at sentence level. We want the correct number of correct words in a sentence. Notice, though, it's a whole field called microscopic intelligibility, which looks at a phoneme level. We're not specifically asking for that, but you might want to use that as a technique as well. The other problem we see with current metrics is they can be overfitted. You know, someone develops this metric, they have a set of data, they work on it, and it works really only best for that corpus used during the development. And that's always a risk, and that will be a risk within our challenge as well. So this is the baseline system that we have been working with, and we provided, John mentioned a baseline system. And essentially what we have here in the bottom left-hand corner is something to generate speech and noise. So this is a room acoustic simulator with anechoic recordings of speech and noise sources. That could be an interferer speaker, or it could be an interfering domestic noise source. We also, everything has to be personalized to the listener. Hearing aids have to be personalized to individual listeners. So we have listener characteristics, and those are mostly, but Mike will talk a bit more about that. They're mostly audiograms, but we have other data about listeners as well. So we have, coming into our hearing aid, we have speech and noise, and we have listener characteristics. Our hearing aid, this is what our entrance provided, so you don't have to worry about this block, but our baseline had a fitting system and then actually some hearing aid working as well. So we'd hope that hearing aid would produce improved speech and noise. So this is, then we get to this prediction model, and that is what you're trying to work on in this prediction challenge. So that we've already got the improved speech and noise provided by the hearing aids. We already obviously have the clean speech because we generated it in the first place. We also have a transcript of that. And what we're wanting you to do is to actually predict the intelligibility score that is produced out of that system. As John said, we already used MB Story. So this intelligibility model was MB Story in our first round. And one thing he didn't mention, but it's very important, is we have a hearing loss simulation, because MB Story is not designed for people with hearing loss. So we used a Cambridge model of the hearing loss simulation, and we also used MB Story, was how we did it in first round. But we're hoping you'll do better than that for us. And it could be that you make one big prediction model for speech intelligibility, so you replace the entire orange block, or you could keep with our hearing loss simulation and add in an intelligibility model. That is up to you, which way you wish to go with it. In general, with intelligibility metrics, there's 2 approaches, and they've got different names. We could call it double-ended, intrusive, non-blind methods. So those are ones where we have knowledge of the clean speech, the original speech, and the speech and noise. And in general, for lots of uses, that will give us a better estimate of the speech intelligibility, because our metric can compare input and output. But there's a whole series of methods which are now called single-ended or non-intrusive or blind, depending on what you want to call them. And that just uses the speech and noise produced by the hearing aids. Now, that's potentially much more flexible because you don't have to have the original speech source. Give you an example of that. One of the common hearing aid processes is to shift things in frequency. Take stuff which is in the band that people can't hear because of hearing loss and shift it down to a band that they can hear. And that doesn't tend to work very well with double-ended models. So there are uses for single and double-ended, and then we encourage both of them. And in fact, if you look at how the rules of the challenge, we actually want both kinds of entries. So do one or do both. Both would be very useful to us. In terms of the intrusive or the double-ended methods, then what we have is you have speech, and this is a spectrogram, or it could be a Mel spectrogram or a cochleogram. So we have speech, and we have speech-shaped noise, or just a noise source, and these are combined together. So this is what the hearing aid is working with over here, is the speech plus noise. And essentially an intrusive model compares this speech plus noise mixture to the original speech in some way. And usually that's done in time frequency sort of bins. And there's various processes you could imagine, mathematical processes to compare the two, which I've listed. So the first one would be correlation. So we could correlate this spectrogram with that spectrogram, compare the two. High correlation means there's a lot of speech visible in the speech plus noise, therefore the speech intelligibility is good. So that's the kind of process. Quite a few metrics use correlation. You have a glimpse-based metric, so you could be looking for where is the speech visible within that speech plus noise spectrogram. Still, that's a glimpse process. You could do weighted signal-to-noise ratios, this sort of SII kind of approach. So look at the signal-to-noise ratios in each of those bands. or you can go to something like the changes in modulation, this sort of speech transmission index approach. So basically, there's a variety of mathematical process for comparing the input speech to the speech plus noise. In terms of non-intrusive, I would definitely recommend reading this paper, which came out it was actually out last year, but it's got a publication date of this year, because it really goes through all the non-intrusive methods, these blind methods, in nice detail. And I'd recommend having a look at that as a starting point. And so the techniques, I've listed some there. You could take a measure of speech quality, a non-intrusive speech quality. That's something that's used. And as you see, ITU, that's a standard method you can even use for that to start with. One other approach is to estimate the clean speech. So take the speech plus noise, use some form of machine learning to denoise it, and that estimates the clean speech. Then you have an estimate of the clean speech. You have the speech plus noise. You can use an intrusive method at that point. I've done a paper with that in that. You can extract features from the speech and noise mixture, which correlate well with intelligibility. And then you can get down to actually starting to use some deep learning if you want. So you could do something like feed in Mel spectrograms of the speech plus noise mixture and expect a machine learning algorithm to extract from that speech intelligibility. And the final approach, which we're seeing as well, is use to automatic speech recognition. Put the speech plus noise into an ASR system. That will obviously give you an estimation of the words and see what the word error rates are like, actually by looking at the transcript or looking at the error rates within the ASR algorithm. So those are broadly some of the approaches. Maybe you have a different one, maybe you have a combined one, but that's a good paper to look at to get a good summary of what's going on. One thing I would say is we're really interested in binaural, because we have two ears, and that makes a big difference to speech intelligibility. And some of the metrics deal with this, and a lot of them don't. One way to do it is the better ear listening. So better ear is very simple, that your brain pays attention to the ear where the speech is loudest. Well, that's fairly easy to put into a metric. What you do is you do the speech intelligibility for the left ear, the speech intelligibility for the right ear, and take the biggest number. That's a kind of typical technique. But then you have binaural unmasking, where the brain puts together the left and right signals, combines them in some way to maximize the speech and minimize the noise. So that's slightly more complicated to model. For example, our MB Story model had a stage to do that in as well. And then if you've got better in binaural unmasking, you need to combine all those processes together. So we're very much interested in binaural listening as well. So if you want to know more about specific metrics, if you go to the Clarity Challenge website for the prediction challenge, you'll find that James Cates has done a really nice talk there about his metrics and some in more detail than I can do today about his metrics and why you might use them. His metrics are HASPI and HASCII, a hearing aid speech quality index, for example. And now I'll pass over to Michael Ackroyd, who's going to talk about hearing impairment and speech prediction. Are you going to run the talk yourself, Michael?
I'm going to try, Trevor. I'm hoping you can see me. My little camera lights come on. Can you see the slide?
Let me just stop sharing screen. Key points and resources I can see. You're not on the first slide.
Yeah, I skipped that part. Thank you, Trevor, for that introduction to all the various models and what it is we're trying to do. I'm going to follow on from Trevor's last slide with key resources and start with some key resources of my own relevant to hearing impairment and speech intelligibility. First of all, I've got a standard paper written by Brian Moore describing the perceptual consequences. And then second, I'd like to point you at a workshop talk given by Carolina Smeds last year, which goes through quite a lot of detail and background about how hearing loss affects the perception of audio signals. Then there's 3 papers which describe some of the additional data that we have on our listeners. We've got what's called a digit triple test, which is where you have to listen to 3 digits in noise. If you get them right, we make it quieter. If you get them wrong, we make it louder, and then we adapt that level until you can just about get them. And then there's 2 papers about 2 questionnaires. The first one called the GHAB, which is the Glasgow Hearing Aid Benefit Profile, and is a standard measure of the benefit that people get from their hearing aids. And then a questionnaire called the SSQ, which stands for Speech, Space and Qualities of Hearing, which is now a fairly standard questionnaire asking people to sort of describe not so much the absolute problems problems they have in listening to speech in backgrounds of plain noise or an audiogram situation, but sort of in more typical situations, such as listening to people in restaurants, or being able to locate sounds, or the timbre of sounds, or the separation of sounds. And finally, and I think it's particularly important, and I highly recommend you look at it. Every few years, there is a multi-country survey done on hearing loss, hearing aid usage, what drives people to take their hearing aids, what means they don't, the proportion that take them up, etc. The most recent one is called Eurotrack, and I've indicated at the bottom right the website for it. So perhaps the main effect that people with hearing impairment notice is basically they just find it really difficult to focus on the sounds they want to hear, especially speech, when anything else is present. It's the inability to separate sounds that really gives the problems. But it's worth noting throughout this and throughout the papers and throughout the challenge that although on average we can say that people with hearing loss suffer problems and those with more hearing loss suffer more problems, always remember that everybody is absolutely unique. And one of the things we're trying to do in the Clarity Challenge is to try to get at that level of uniqueness. Two people with exactly the same hearing loss might not necessarily understand exactly all the same words in exactly the same way. Right, how do I move forward? Right, so across this talk, I'm going to summarize some of the psychoacoustic phenomena that have been associated with hearing loss and are all sort of implicit in our abilities to understand speech. Fairly obviously, it's reduced audibility, especially in the higher frequencies, and that defines the hearing loss as you would have it measured in clinical audiometry. And also fairly obviously, there's an increased signal to noise ratio for speech and noise as measured by some speech tests. Now, I'll come back to the other four in a moment, but for the moment, I just want to talk about signal to noise ratio. Copied here a paper from 15 or so years ago now that links the pure tone average hearing loss on the x-axis to people's ability to do speech reception in noise. The left-hand panel is for plain speech spectrum noise, but the right-hand panel is for modulated noise that, give or take a bit, approximates the modulations you would get in standard speech. I'm going to go through some of the standard terms because these are terms that you will come across when reading papers about hearing loss and audiometry and hearing impairment. So by pure tone average, which is the x-axis, we simply mean the average of the audiometric loss at 500, 1000 and 2000 hertz, because on the whole, they're the ones that are most important, that represent fairly easily the speech frequencies. The audiometric loss is a clinical definition. It's the lowest level of a single pure tone that you can hear in a clinic, in a soundproof booth, as measured by an audiometer and by an audiologist. Then that converts to dBHL, and the way we measure it is it's in decibels worse than normal hearing reference population. It's not quite the same as dBSBL because it turns out that normal hearing is not necessarily perfect at every single frequency. So by dBHL, what we mean is how much worse somebody is compared to the ISO standards of normal hearing for reference. The SRT is the signal to noise ratio of the speech and the noise, at which you get half the words correct. And then the MAR score, as I said in the two panels, is either speech spectrum, speech shaped noise or unmodulated noise. Now, on the whole, you can see that people with bigger hearing losses have higher signal to noise ratios, but you can also see that there is a fair amount of individual variability. It's also worth noting that the effects of hearing loss are much worse in the modulated noise. You've got basically a 12 dB or so difference from normal to impaired in modulated noise compared to only about 4 decibels in plain noise. What that means is that hearing impaired people aren't able to take as much advantage of the gaps and the dips in modulations as people with normal hearing, and that's one of the factors that contributes to their inability to separate speech. Just in passing, as hearing audiometric speech scientists, we tend to throw decibels around with abandon. Try to sort of give here some indication of just what 4 decibels is actually really like to a person. If you sort of convert it to a distance by using the inverse square law maths, then it's like if you've lost 4 dB of signal noise ratio, you've got that whoever you're talking to has got to be nearly 40% closer to you. If it's modulated background like the infamous cocktail parties, they've got to be something like 75% closer to you. If instead you convert it to like a signal to noise ratio in terms of like the number of potential maskers at your cocktail party, and you put them in semi-random positions around you, then in this case, sort of normal hearing, you could cope with 8 interfering talkers, but with hearing impairment, it might only be 4 or even less number of talkers around you. So clearly this is going to matter, this is going to affect you, and then hearing impairment causes lots of downstream problems. It's now being linked to social isolation, and there's strong indications that it's also linked to later life dementia. And there's much research going on at the moment to try to work out the directions of causation and to see if hearing aids actually are an early way of sort of preventing later life dementia. But back to the psychoacoustics. So I've mentioned about audibility and increased signal noise ratio, but with hearing impairment, you also get reduced frequency resolution, you get reduced temporal resolution, be it temporal fine structure or envelopes, or like I've just indicated with modulation, dip listening, you get reduced temporal integration, you get reduced spatial hearing, whether or not the ability to locate sounds, or the ability to separate sounds using binaural unmasking. So there's many papers across all the years that have linked these to speech perception, and there's correlations that indicate all of these mostly to a medium extent have some relationship with ability to understand speech. There's also another one which is not necessarily directly related to speech, but is of absolute practical importance when designing a hearing aid. And that's that you get a steeper rate of change of loudness as you increase level, but there isn't much change in the level at which sound becomes uncomfortable. What that means when you link that to the reduced audibility in the first place is that you get a much reduced dynamic range between unable to hear and painfully loud. So if you take an ideal normal hearing person, their minimum level they can hear is about 0 dB. Somewhere around 120 dB, it's going to become painfully loud. So they've got 120 decibels worth of dynamic range. Somebody with hearing impairment might only have about 45 dB of audibility, but the uncomfortable bit is still around 120. And it's this that causes a problem. If it wasn't for this, we could simply put in simple plain amplifiers that turn the whole world up. But because you've got this reduced dynamic range, you have to put in compressions in order to ensure that sounds at sensible volumes, when amplified by enough to make them more audible, don't then become painfully loud. So in terms of what hearing aids basically do, and effectively a hearing aid is an amplifier. It's a really fancy amplifier. There's an awful lot of computation going on in it, but basically it's an amplifier. What you do is first of all, you amplify by an amount that is dependent upon the actual hearing loss as measured by the audibility or audiogram. The particular numbers are set by prescription formulae. You'll come across terms such as NAL, RP2 or CAMFIT or DSL or various others. But that's what an audiologist would do. They'd measure your hearing loss, and then they would set the amplification of your hearing aid by some prescription formulae. But then you need to vary dynamically the amount of that amplification, and it's got to vary dynamically with the level in order to compensate for the reduced dynamic range, which is compression. And then you have to start worrying about what time constants do you run the compression? Do you need to do, is it fast compression or is it slow compression? What range do you have the compression over? And many other parameters that go into actually designing a real compressor with a real amplifier that works almost instantaneously in somebody's ears. So that's what hearing aids are doing. But what is perhaps more interestingly, it's what they don't do. What they don't do is they don't restore normal hearing. They don't make sound natural or transparent. They don't distinguish actually what people basically wanted the hearing aids to be able to do in the first place, which is to help separate the wanted versus the unwanted sound, or to really try and get on the ability, the talker they're wanting to hear while in the background of everybody else. To be honest, most clinicians don't fit a hearing aid with much else than an audiogram. And what they also don't do is directly address those quality of life concerns that hearing impairment can cause, which is that there is still a stigma from wearing a hearing aid. And a lot of people, when given a choice of hearing aid, say, can I please have the smallest one or the one that is most hidden? Hearing aids can hurt. in the sense that the actual mold that goes inside your ear, if it's not made exactly perfectly, it's going to hurt a little bit. The fact that often people wait too long. It's the standard number is that people generally wait 10 years longer than they should do in order before deciding to take up a hearing aid, plus the lack of counselling and the lack of general follow-up. So you could argue that actually what current hearing aids aren't doing is what the people are wanting, which is about wanting to be able to distinguish the sounds and to be able to get at all of the speech perception problems and sort of try and bring in the things about resolutions and spatial hearing and integration. Although what they do is they do make sounds audible in the first place. So that is still a bonus, and I'd still highly recommend if anybody out there have an older relative who is not sure about what their hearing is like, or their partner says you're turning the TV up, or they're having to repeat things, please go and see a clinic. Please go and see an audiologist, because on the whole, a hearing aid will improve an awful lot of what they do, but they're still not as good as what they can be on speech perception. And that underlying is why we're trying to develop these clarity challenges. Thank you, Trevor.
Well, thank you, Michael. I don't think it's me next, though, is it? I think it might be back to John.
So thank you, Michael. Thank you, Trevor. Hopefully, is my screen being shared again? Clarity Prediction Challenge.
I can see that clearly, John.
Brilliant, thank you. So yeah, I now want to return back to some of the specifics of the challenge, talk through what we're releasing, what the rules are, what the data is, and what entrants need to do. So yeah, as Trevor's pointed out, the full process looks something like this, with a hearing aid model on the left and the kind of prediction model on the right. So this challenge is focusing on the prediction model. You're going to be given signals that have been processed by hearing aids. You're going to be given responses that from hearing impaired listeners listening to those signals. And your job is to produce this kind of orange piece on the right, which actually kind of predicts the intelligibilities of those listeners for those signals. So the timeline is something like this. We launched initial training data and initial tools back in November the 16th. Then on January the 1st, we launched a baseline prediction. In March, we're going to launch final evaluation data on which you can actually evaluate the systems and compute your scores. And then we've got the submission deadline, which is on March the 21st. We're pleased to announce that there's going to be a special session at Interspeech called Special Session on Intelligibility Prediction for Hearing Impairment, which is going to be used to kind of showcase the challenge. So people submitting to the challenge will be able to submit also Interspeech papers. The deadline for that is March the 28th. But in conjunction with the Interspeech special session, also holding an online workshop. So we'll have a workshop event in June, and people will be able to submit workshop papers to that in April. Just to be clear here, so when you take part in the challenge, you can submit a workshop paper, you can be involved in the online workshop. If you submit papers to Interspeech, the Interspeech conference has got its own review process. If those papers are accepted, they'll be accepted into the special session. So everyone taking part in the challenge will have an opportunity to present at the workshop. People who have had papers accepted for Interspeech will be able to take part in the special session as well. And just on that note, the special session won't be just for the Clarity Prediction Challenge, but it'll be wider. Anything related to the challenge, anything related to intelligibility prediction or hearing impairment will also be kind of acceptable into that session. So that's the kind of timeline. So I want to talk a little bit about the data that we've released and what we're asking people to do. So the data we've released is composed of pairs of signals and listener responses. So a signal is a scene containing a target sentence that has been processed by a hearing aid algorithm. And a response is the percentage of words that were correctly recognized by a hearing impaired listener when presented with that signal. So all the signals are coming from the output of the Clarity Enhancement Challenge, where we had a number of teams processing these scenes with their own hearing aid algorithms. So you're going to be provided with pairs of training examples, which you can use to learn from. So pairs of signals matched with the responses. And then in the evaluation task, when the evaluation data is released, you'll be given a set of signals and characterizations of the listener and told to predict the intelligibility of that signal. You'll submit those predictions and then we'll evaluate them and return to you your score. So just to explain a little bit about the signals, there's kind of three factors in the data. So if you think about the signal, there is the scene itself, which is the sentence that has been spoken, the interfering sound, the environment in which it's been spoken. There's the hearing aid algorithm, which is the algorithm which processed the scene before it was presented to the listener. And of course, there's the listener. So for each kind of signal intelligibility pair you get, these are the three factors in the data. So I'm just going to speak through a little bit about how these are presented to you. So first of all, there's going to be two settings. There's going to be a closed set setting and an open set setting. By closed set, what we mean is that the evaluation will use the same systems and listeners that are seen in the training data. So you think about your training data where you've got your signal response pairs. The systems, that's the hearing aid systems, and the listeners that you see in training will be the same ones that you see in the evaluation. In the open set, which is more challenging, when it comes to evaluation, you'll be seeing different listeners and different systems than you saw in training. So in the first one, I guess you can make systems which are specific to that listener and specific to that hearing aid enhancement. In the open set evaluation, you've got to make systems that will predict and generalize to unseen things. So the responses that you'll be provided with. So this is what a response looks like. So in the data, you'll see a number of JSON files. You'll see the two sets for training, one called cpc1.train.json, which is for the closed set, and cpc1 train-independent.json, which is for the open set. Within the training data, what you'll see is a number of entries like shown below, where you've got a description of the signal and then the response that was returned by the listener. So what you'll see there is for each signal, you'll see a scene ID, and that will be linked to the identity of the scene, and I'll show you how that scene is described in a minute. You'll see the listener ID, which is the identity of the listener that's going to listen to this scene, a system ID, which tells you the identity of the hearing aid system which processed that scene. Then you'll see the sentence, the transcript of the sentence, which is embedded in the scene. So in this case, it was, I suppose you wouldn't be free for dinner this evening. So that's what the hearing impaired person was meant to hear. Then you'll see the response, which is what the hearing impaired person actually responded in the listening test. And in this case, they just responded with freeze evening. The number of words is number of words in the prompt. Hits means number of words that were recognized correctly. So in this case, they've only got one word correct here, which is evening. And then you can compute a correctness percentage, which here is 1 word out of 10, so 10%. So the number you've got to predict here is 10% of the words are recognized correctly. The last line here gives you an ID of the file which actually contains the signal. So this is the file ID with the signal in it. So this is a single response file, and in training you'll have about 4,000 of these. When it comes to evaluation, there'll be another 1,000 to evaluate on. So just to talk through what the scene, the listener, and the system data look like. So first of all, the listener. So going back here again, you'll see here the listener ID was listener 0239. There were a panel of listeners. There were 28 listeners altogether. Each listener's got their own audiogram. So there'll be a file called listeners cpc1 train.json, which contains descriptions of the listeners. You'll see a number of listener IDs like this, and for each listener ID, you'll see the name of the listener and their audiogram, where the audiogram tells you the center frequencies at which the audibility was measured at, and then for the left and the right ear, the hearing loss in dB. So that's a characterization of each listener, and there'll be one of those for each listener in the training set. Now, on top of that, there's a spreadsheet in Excel format, which contains all the other data that Michael was talking about, the digit triple test data and the questionnaire data for each listener. So you've got kind of full exposure of all this data for every listener in the listening panel. Then the scene descriptions. So this describes the actual kind of scene in which the signal is presented. So this has all been simulated. So people have been processing simulated scenes. We're using a room acoustic simulator called Raven. So for each scene, you'll have a scene ID, just going back again 2 steps. In the responses data, you see the scene and you'll see the scene ID. This one here, for instance, S08510. In the scene file, you're about to link that to a description of the scene. So here for scene 00001, we have all the metadata for that scene. So this means things like the room dimensions, the SNR that the signal was at, the head-related impulse responses for the listener who was listening in that scene, the positions of the target, positions of the interferers, and so forth. So the whole description of the scene is contained in that scene file. And then finally, the system descriptions. So there are a number of systems. These are all the systems that were submitted to the enhancement challenge. For these, there's no metadata file, but what you've got is you've got a system ID. These are kind of E02, E03, and so forth. And if you actually go back to the Enhancement Challenge workshop, you can find a lot of information about these systems because people presented papers on them. So you can kind of find out kind of what these systems are doing. There's a little overview talk linked here at the workshop. A quite nice summary here showing you kind of for each system, breaking it down into the kind of beamforming they were doing, the noise kind of separation they were doing, and the hearing loss compensation. So you can see there's a number of different types of systems that were submitted. Some were doing kind of traditional kind of beamforming using different types of beamformer. Some were doing kind of deep learning kind of noise removal. And they were all doing some sort of hearing loss compensation. But those descriptions give you some idea of perhaps what these signals will sound like, what kind of distortions they may have, in what conditions they may have done well, and what conditions they may do badly. So that data is all available as well. So during the training, you basically got access to everything, you know, that went into making this prediction. So on top of this, you are provided with a number of audio signals. So obviously you've got the output of the hearing aid processor. So this is the kind of noisy signal that the hearing impaired person listened to. So that's probably the most important thing. That's going to tell you, you know, this is a thing you've got to actually predict the intelligibility of. You've also got the target signal convolved with the anechoic room impulse response. So as Trevor was saying, for intelligibility measures, there are kind of these double-ended and single-ended approaches. Where you've got your double-ended approaches, you're using a reference signal. So this provides you the kind of clean reference that you can use in your intelligibility prediction. And then during training, there were a number of other signals, basically a complete breakdown of all the signals that went into the simulation of the mixed scene. So these are all provided for you during training. So training and development. So during training, teams can use signals and listener responses provided in the 2 training sets. So the JSON files describe the list of signals that you can use. In addition, teams can use their own data for training or expand the training data through simple automated modifications. So by this, we mean that if you've got other intelligibility data you want to bring into the mix from previous evaluations, you know, if you want to kind of build on previous research, that's absolutely fine. If you want to kind of remix some of our data in some way, that's also fine. The only thing obviously you can't use is the kind of evaluation data that we're going to be using to do the final evaluation on. Yeah. One thing we haven't done is we haven't defined a specific development test set. So we've got an evaluation set which is hidden, which you'll evaluate on. We've released training data, but we haven't split it into kind of a standard training and development set. So you can't compute a standard kind of development score. We're allowing people themselves to kind of decide how best to split the training data. So one thing you want to do is to kind of, is to evaluate as you design your systems. You'll want some sort of development data to do that with. But how you split the training data into your kind of training set and development data is kind of left up to you. So you can do so in such a way that you don't kind of overfit. But that kind of preventing kind of overfitting is kind of, I guess, one of the problems here. So we've kind of rather been prescriptive about that. We're letting kind of entrants decide how to do that themselves. Then evaluation time, we'll release the evaluation data. Then at evaluation time, models can use the output of the hearing aid processor. They can use the reference signal. They can use the IDs of the listeners that are being assigned to the scene. So they can use the audiograms of the listeners and the metadata that's been provided to the listeners. And that will be all they can use. And then you will, from that data, make a prediction at a sentence level for the intelligibility of that sentence. And you'll submit those predictions to us, and then we will score. Those predictions. Baseline code has been provided on GitHub. So on GitHub, there's a repository called clarity_cc. This is a single repository now that you're using for all our Clarity challenges. So if you go on today, you'll find at the top level a directory called Clarity CEC1, which is all the materials for the previous enhancement challenge, and Clarity CPC1, which is the current prediction challenge. So you can install that, and you'll have actually everything you need from looking at the enhancement challenge and for taking part in the prediction challenge. If you look into the prediction challenge directory, you'll see tools for actually running our baseline system. If you look in there, you'll find Python scripts. There's basically 5 stages here. We have 5 little Python tools and a Python script called Python run all, which will run them all sequentially and end up producing a prediction score from the training data. So just to run through these 5 little stages, there's a little script called check data, which simply checks the integrity of the data to make sure you've got it all installed correctly. Then there's run HR processing, which actually, so our standard prediction model baseline here is based on the MB story that we were using for the enhancement challenge. So what we've got here is we've got a hearing impairment model, which is the Cambridge Group MSBG hearing loss model. So this runs a signal through a hearing loss model, producing a kind of version of the signal which is meant to simulate what a hearing impaired person would hear. We then pass that through this intelligibility model called MB story, which takes the reference signal and the hearing impaired signal and produces this score on a scale of 0 to 5, the MB story score, which is meant to predict intelligibility. And then there's a little stage here called predict intel, which maps the MB story score onto a kind of percentage of words correct score. So it's taking a little sigmoid function through the MB story score on a scale of 0 to 1 and mapping it onto this intelligibility score of 0 to 100% words correct. And then finally, this report RMSE score actually computes the error metric that we're using for the system. So all systems are going to be evaluated by the RMS error metric. So this means that we look at the predicted percentage intelligibility, compare that with the true intelligibility, compute the error, and then do the root mean squared errors across all the sentences in the test set. So you should be able to install this and simply type Python free run all, and it will run through all this and produce this intelligibility score. In fact, the hearing loss model, and intelligibility prediction are a little bit slow. So when you download the data, it kind of pre-caches pre-computed MB story scores. So if you run this as it is here, it will just use the MB story scores and immediately produce you a RMS score. Or if you like, you can ask it to run through the whole pipeline, sticking the signals through the hearing loss model and the intelligibility prediction as well. I haven't got the score here, but the baseline score, I believe the RMSE score is something like 36%. So it's quite a long way off from zero. So that's kind of the baseline score which you have to beat. And that's reported on the web page. Just to kind of run through again the submission timeline. The evaluation data will be released in March. So this is when we actually release the evaluation signals and the paired listeners. You'll have a few weeks then to make your submissions. So teams submit their predictions, i.e. the kind of percent words correct per signal for both track 1 and track 2. We will be able to return scores to you almost immediately because evaluation doesn't take any time at all. We'll have your percentage words correct. We simply compare that with what listeners said, and we can return your scores to you. That will be automated, and we will return those within 24 hours. Teams will then be able to submit asked to submit a draft technical report. That'll be useful to us just so we can check that teams have kind of obeyed the rules of the competition, and we can ask any questions if we're unsure about that. Then a week later, on the 28th of March, is InSpeech submission deadline. So this is where teams are encouraged to submit their work to the InSpeech for presentation in the special session that we're organising. So that's a 4-page paper submission. And then a bit later, on the 28th of April, we've got the Clarity Workshop paper deadline. So this is a kind of separate event. The Clarity Workshop, will be a little bit more informal, a bit more relaxed. Everyone who's taken part will be accepted into the workshop. The paper format doesn't have to be the InSpeech paper format. It might be, you can submit an extended abstract or something longer if you wish to. And then in June, we will hold the Clarity Online Workshop event. At this point, we will announce the results and the team rankings will be revealed. And then in September at InSpeech, we'll be having a special session where we'll be reporting on the prediction challenge. Papers that have been accepted to InSpeech will be presented. And there'll be a kind of a broader discussion there on intelligibility prediction and hearing impairment. So I think that is all I've got to say. So thank you for listening. I'll leave that slide up for a minute. So you've got any questions, you want any further information, these are the kind of contact points. And I think now the plan is to kind of open things up for a Q&A. At this point, I'll pass back to Trevor.